many of them. You need many, many of them. And that's why when I started this, then I told you this correlation was a mistake. Finley has the correct physics. There is a difference between tension and torsion loading. And this difference is the normal stresses that acts on cracks. And so, of course, the octahedral stress works better, right, because it's smaller in torsion than it is in tension. Okay, but it's a mistake. It's a mistake. Yeah. Okay, so that's the Science model and Finley's model. The other model that has widespread use is the Dang-Van model. I don't know why. It's an interesting model. So Dang-Van is a French guy, more or less. Obviously not from his name, but in French. And well, you know, there are different ways of looking at fatigue. Right? In the French models of fatigue, the mathematics must be elegant, but it doesn't have to work. But the mathematics must be elegant. Why are you laughing? Do you agree? Yeah. Yeah, okay. A Polish model of fatigue, my friend Gregor Glinka, right? The mathematics must be correct, not necessarily elegant, and it should work. American models of fatigue, there must be a nice color picture of the results. There's no requirement that they work, but in the end there must be a very nice color picture for the report. German model of fatigue, it must give the correct answer. You laugh about that. It's true. It's true, and I'll tell you why I can say that. The people from FemFat, like Steyr, is that right? Yeah, Steyr in Austria, came to see me some years ago when they wanted to enter the American market with their fatigue software, and they talked with me and they told me how accurate it was, and they showed me test case after test case and so on and so forth. And so they wanted me to give them some advice on how they could, market this to the American people for buying fatigue software and so on. And I told them, I said, none of this matters. I says, if it doesn't fit in the finite element software they are using to make nice color pictures, they won't use it. They just won't use it unless it's part of the computer process. And the people from Steyr, they looked at me like, well, how can this possibly be? Accuracy is the most important thing. But that's really not true in a design office, right? In a design office, for people who are using this, the most important thing is that it's easy to use. If it's easy to use and accurate, that's a bonus. But easy to use is first, and so that's when I start using the terms the American model. There must be a nice picture first. So it's true. It's true. Anyway, so Dang-Van has a really nice, elegant model, and it's based on the idea of isotropic hardening. I don't think I have a picture for that today. Just let me look. Yeah. So isotropic hardening. So you know that if you just load a metal and I load it and something like that for the stress and the strain, and of course it has its original yield point here, and then I unload this to here, and then when I reload it, it does not yield until I reach the stress level here. I've essentially made, because of plastic deformation, I have essentially made the material stronger. I'll talk about this a little bit more later. And that process is called isotropic hardening, and you recognize that as a strain hardening. The more I cold work something, then the stronger and stronger I make it. Okay, that's the phenomenon. And what Dang Van said was, okay, I have micro and macro stresses. True. Right? So if I look at this bar, then I want to know what is the stress. Okay? We do an experiment. Right? I load this bar, and I'm going to make the problem easy because that's what professors do. So when I see this bar, I see an area of 1. Okay? And now I'm going to load this, and I'm going to load this with a force of 10. Okay? What is the stress in this bar? 10. How many think 10? You? What about the others? Are you too tired? I mean, you've learned to sleep in place? I mean, I know that happens with students. Yeah, what is the stress in the bar? Okay. Yeah, 10 could be an answer. How about 5? How many think 5? No takers. How many think 0? No takers. Well, why not? I like 0. I like 5. Look. Yeah, sure. Right? Depends on where I look. Right? I load this with 10, and of course those who want 10 say, well, sure, I want to know the stress, but remember, you know, stress is really not a scalar. Stress has direction associated with it. Stresses act on planes, and so if I think about a plane like this, of course the tensile stress on that plane is 10. And if I think about a plane which is oriented 45 degrees like this, then the stress is 5, both the tension stress and shear stress. And if I need 0 for the answer, then I choose this one. So I can, you know. I told you I am tricky. This is how I win all the beer from the undergraduate students I teach. Very easy. Very easy to win these. Very easy. And yeah. Yeah, you have to be a little careful. I have to be a little bit careful. You know what I mean? I can't go too often with them. They have much more stamina than I do. So, okay. So, all right. But let's think about this now in a little different way. That's just calculating macroscopic stresses. And that's Dang Van's idea of the macro stress. But now think about this, that this bar is filled full of crystals. 1 millimeter cubes are the different crystals. And of course, each of these crystals will have a little bit different orientation. And that means that the stresses in each crystal will be different. And so if I load this with my force of 10 here, acting on this unit area, the average stress in all crystals in this direction is 10. But if I look at each individual crystal, then the stresses are a little bit different in each individual crystal. Okay? But since fatigue is a weak link process, whatever crystal is the weakest or sees the highest stress, however you want to look at it, this is the one that will crack. And this is Dang Van's elegant idea. It says, fine, when you do modeling, you calculate this macroscopic stress, and so I'll just use sigma and epsilon, the uppercase ones. This is this macroscopic stress. This is the 10. But then, each individual grain or crystal will have a microscopic stress of sigma and epsilon. Of course, it's strain as well. And if, through the loading process, this grain may have some initial plastic deformation, but if it isotropically hardens so that there's no plasticity, you will not get fatigue failures. If it does not isotropically harden to 0 plasticity, then this will eventually nucleate a fatigue crack. That's his idea. So the next part is, well, okay, how do we go from these stresses to these? So to do that, then we need a little bit of mathematics, and we need some very elegant mathematics in it. And so we develop a 3-dimensional plasticity model. And this is a 3-dimensional plasticity model based on Orwin's dislocation theory. And, okay, the best way to explain this, I can't. Think about that I have three principal stress directions. And of course, if I did a tension test in any one direction, then I would get the yield point here, and I would get the yield point here, and I would get the yield point here, right? And now think about that I can do this in multiple directions, and that is I can test by pulling in sigma 1 and sigma 2 at the same time. And if I do that, then the yield surface becomes a sphere which is centered around the origin. Okay, and that gives me all combinations of the three principal stresses that will cause yielding. Right, so I have this sphere on the origin. And the sphere initially will have this radius. Okay, the initial yield sphere. And now I let this plastically deform. And I use my elegant mathematics. I do have to admit to you that at one point I did derive all of that. And I got exactly the same answer he did. You know, these are exercises professors do just for fun once in a while. Okay, so then we have to worry about things like mean stresses and so on, and these spheres can move around in space, and so these things move around in space, but as I continue to load it, these spheres, which just give me the combinations of stresses and moving around in space, also expand in size as I do it. And that essentially corresponds to keep increasing the radius, right? And the idea behind Dang-Van's theory is that I just need to know what is the critical distance here, what is the critical stress range that I can have, and that will be dependent upon the history. Right? How big this sphere can grow. That's the basis of it. Right? And then you need a fatigue theory with it, and his fatigue theory is to look at the maximum shear stress plus a constant times the hydrostatic stress. And this is the mean stress. And this line then gives you the combinations of shear stress and hydrostatic stress such that if you are inside the lines, you do not get failures, and if you're outside the lines, you do get failures. Okay, that's the basis of the theory. And it works reasonably well. A lot of people in the automotive industry use it. But at the end of the day, all right, let's just compare these three ideas. So you remember, we really have three conceptual ideas for the fatigue theories. And as I mentioned when I started, all the other 100 models out there, I can probably put in one of those three classes, right? Science was completely empirical. I did the experiments, and he just found some math that matched it, right? No critical tests. Finley's was based on this idea about cracks and normal stresses helping open the cracks, right? That was his physics. And Dang-Van's idea was based on the physics of hardening of an individual grain, essentially plasticity in it. But when you look at the theories, right, they're all pretty much the same in their mathematics in the end of the model, because look, science criteria chose the octahedral stress, and then he made a modification because of hydrostatic stress. Fine. Science says, oh no, it's not this one. You should really use the maximum shear stress, and you should modify it by the maximum stress acting on that plane, not the hydrostatic stress. Okay. What's the difference, first of all, between these two? Well, the difference is that in the case of a mean shear stress, right, Finley's model would say that a mean shear stress has a small effect. And science says, no, my observation says it didn't have any, right? But the effect turns out to be pretty small. But it says there should be a small effect. And so you'll see some small differences in these theories. But in a general load case, they give about the same answer all the time. In my own software, I always plot out all the different answers, and you have trouble finding histories for which they're different. And Dang-Van's criteria essentially uses this, the maximum shear stress from Finley, and the hydrostatic stress from science. And it goes back to what I said in the beginning. I only have two variables, right? When I look at all these experiments that were done in tension and torsion, I can do something with the tension stresses, and I can do something with the shear stresses, and combine them how you like. Combine them how you like. But these three models are okay, and they work, and the derivatives of them. I guess we could have a second order model of some sort. Right? We could have a second order model, then we could take the square root of this quantity and all kinds of things like that. That's what you see. That's what you see. All right. So I just want to make a final note before leaving the stress life models, and that is how different are they? And right, there's signs in Finley, there's torsion, there's tension, there's biaxial tension, and I just look at doing this for the Goodman diagram, and this is essentially doing something just considering the tension stresses and the other two shear models. And what you see, in the case of tension, of course, they're all the same, right? Because they're all normalized to the tension fatigue limit. As you go into biaxial tension, then what you find out is that science criteria tends to overestimate the life usually. And that's because it's based on equivalent stress. You remember that. All right. If I plot sigma 1 and sigma 2, and I draw the yield ellipse for Mises, then you know that the Mises yield ellipse goes up like that, and back down like that, and that you have this increase in stress right there in the middle, and that's what this is. Okay, so it tends in that case of half a biaxial tension ratio of 0.67 gives you the maximum. And of course, huge differences in shear. Huge differences in torsion, whether you only use the tension stress, and like I say, Finley's and science gives you box. All right. So next I want to do the strain things, and then do some example problems. Which one is open? No. Oh, you make that so easy. I can't use this version of PowerPoint. I told you I got to be very good at PowerPoint when I was sick, and so when the 2007 version came out of Office, I loaded the 2000 version of 7 into my Word 2000 Office and PowerPoint and so on into my computer, and then I started to do some PowerPoint things, and I wanted to do something very simple like put an equation into PowerPoint. And it wouldn't do it. And so I said, oh, what's wrong? And so I looked it up online. The suggestion is type your equations into Word and then paste them into PowerPoint. And so at that moment, I eliminated Office 2007 from my computer and went back to Office 2003 because, of course, the professor teaching always does equations in his PowerPoint slides. And so go into Word. And so I have never learned to use Word 2007. And I'm afraid to try Word 2010, but I suspect that small annoyance has been fixed. Maybe you know that it has or hasn't, and so on. So I'm more or less confused by PowerPoint 2007, to be honest. Okay. All right. So that's the background between the stress-based models. Now I want to talk about the background between the strain-based models. And well, you know from yesterday, I like to talk a little bit about the history. And this is work from Jenkin. And Jenkin was Griffith's professor, actually. And this is, I just have it verbatim. The Engineer was a German monthly newsletter. And so this was a publication that was 4 or 5 pages that was circulated to the Engineer. You can see the time. And this is what he wrote. 6 months ago, I wrote a paper, knowing I would be busy in the autumn. Right? Well, that wouldn't happen today. right? If the paper was due 6 months from now, we might start on it 5 months from now. So that's a problem. Okay. Maybe 5 months and 2 weeks. I don't know. And then I made a model to illustrate a point in it. Right? Fine, we do that. Right? We're writing a paper, we want to make a model. And then as I played with the model, it grew too strong for me, and it took command. And I've done nothing else. Right? That's a good lesson for PhD students. Sometimes you make the model and you play with it for a long time because it's very elegant and you get very nice things out of it, and that's what happened to him. But you know, the bottom one is important is because it explained the whole of my subject fatigue. A pretty strong statement when you think about it. Right? So I made a model and it just explained everything. Right? It just explained everything. Right? And what was that model? Right? Actually, it was a stress strain model. So this is the first publication of the stress strain models, and it's not fundamentally different than what we do today in doing simple modeling. And what he did was, of course, I have a little loading history like this and so on, and I look at the same strain level and I look at what happens for the stresses at points A, B, C, and D. And what you see if you actually plot out the deformation looks like this. And this is what Jenkins was able to do. And of course, you see that depending on where you are in history, at the same strain level, you could have any stress. And what Jenkins was doing in his modeling is he showed what happens if you have a tension overload on something. And they knew experimentally that if you had a tension overload on something, that in fact the fatigue life would go higher. But he was able to show, well, the reason is because you get all these compressive residual stresses after the tension loading. And he was able then to quantify the magnitude of those and do all that kind of stuff. And so he really got the importance of stress in the process. And you know, we've really been using that for the last day or so, right? Because I have been talking about what we see about all these microcracks, and we think about stresses opening the microcrack. It's not the strains, but it's the stresses that open that microcrack. Right? I could have compressive strains and tension stresses. No problem. Right? Just think of a point back here. Right? I have strains which are in compression, but I have tension there. And so if I had a little microcrack that was there trying to grow, it would grow because I have tension across that crack. Okay, that was what Jenkins did back in the 1920s. By the way, that was all lost too. I don't know of any other work from Jenkins' work in the 1920s, and the next work came really in the 1960s. During the interim, nothing. And in the 1960s, it came, of course, because of the computers. You know, you could build more elaborate models and so on, but they were pretty much the same. Okay. Other things about stress-strain response. So I'll take a few minutes at the beginning just to talk about the response of materials. And okay. So this is a busy matrix. You of course recognize this. It's the elastic transformation matrix and the relationship between stresses and strains. And what I want you to note from this are all the zeros. And so if we think about the normal stresses, then the normal stresses are related through the modulus and of course Poisson's ratio to all of the normal strains, but there's no coupling whatsoever between the normal stresses and the shear strains because they are all zeros. Okay? Similarly, the shear stresses, right, of course, are related directly to the shear strains. But unlike tension, there's no coupling between the three shear strains and three shear stresses. Right? They all act independently. Right? Unlike tension, where there's a certain coupling between the X stress and all the other strains through Poisson's ratio. And then, of course, there's the same way. There's no coupling between the shear stresses applied and what the normal strains are. And this is what happens in the elastic solution. So what that means, of course, is that no matter how I twist this bar, it never gets longer. Okay? If you do an elastic plastic solution, right, you start to get plastic deformation. This matrix becomes fully populated. And what that means is that if I have this bar and I plastically deform the bar, then it is possible for the bar to get longer during plastic deformation. but only with plastic deformation can the bar get longer. This turns out to be an important problem in things like transmissions. So you actually get, in some transmissions, the shafts grow in length when they start to get plastically deformed. Okay, so that's what the theory says and what we observe. The next thing is to talk about yield surfaces. So I've already drawn one, and you are used to seeing the Mises yield ellipse, and so that's what it looks like in 2 dimensions. And you can use the maximum shear stress, and that's the Tresca criteria. And the maximum shear stress, of course, it just replaces this by straight lines. And if you actually look at the data for yielding, it will come as a surprise to no one that all of the data scatters in here between the 2 lines, right? So one is not clearly always better than the other. And I would like to take this same kind of data, but I have trouble looking at the ellipse, and so I simply want to take this data and I want to look at this same theory, but I want to look at it as a circle. And if I want to look at this as a circle, right, and I want to do that because I want to look at a plane that's subjected to shear stress and normal stress. And if I normalize this by the square root of 3, that's the Mises criteria, then I can take this and essentially make it a circle in this plane, and so we'll deal with little circles. Okay, just to help us visualize what happens. And of course, we can write down the equations if we want. Then we have an equation of yielding, and in the case of Tresca, there are 3 of the criteria. It's just the 3 sets of straight lines. And if you have Mises, then it's one equation with all of these square terms. Now, one of the things that you will note in this is that when I write the Mises criteria here, then I never have a z stress. Why not? Right? Well, let's just think about what we saw yesterday. Yesterday I said, fatigue always starts on the surface. And I know that the surface direction then is a principal direction, and the value of the stress there is 0. So it makes my life a lot easier if I recognize that one of the principal stresses is 0, and now even if I have a 3D problem, I can solve it in 2D, and so I just write the equations like that directly. By the way, you can do this now in 3 dimensions if you wish, right? You don't have to, but you can. And in the case of the Mises criteria, it's a cylinder. Tresca's a hexagon, and in my funny space, we call it the pi plane. Then it actually becomes a sphere. So you can think about this in 2 or 3 dimensions, depending on how you want to do it. And now I already mentioned isotropic hardening, but we look and see what happens. And that when I isotropically harden something and deform it, then I load this like this, and of course if I unload it and reload it, it says that the strength gets bigger, and if I reload it again, then the strength gets a little bigger, and if I unload it, then I'll get a path like that. And if I look now what's happening in 3 dimensions, right, then that essentially takes these yield surfaces, and again I'm just going to use the 2-dimensional version because it's easy to point to. And what's happening, right? Well, what that says is that I'm going to load this, and maybe I have an original yield strength of 10. And I plastically deform this to a stress of 20. And so now the yield surface has grown and has become twice as large. So if I were to pull this first in tension, and it yielded at a stress of 20, and then I went back to 0, and then I twisted the bar. When I twisted the bar, then it would yield in torsion at a stress of 20, not the original yield strength of 10, because I've hardened this in all directions. Right? So hardening happens in all directions at once. Right? And I could have twisted it in torsion first, and if I strengthened it in torsion, it would also be stronger in tension. And that's this idea of isotropic hardening. It hardens everywhere in it. And of course, depending on what the material determines what the rate of hardening, it determines what the final saturation will be and things like that. But all materials will have some initial hardening to it. And this is why what I showed you then, what's going to happen in fatigue if you work an isotropic hardening model that maybe when I load something on the first cycle, I'll get some plasticity, but it becomes stronger. And then when I load this in compression, it will get a little bit stronger yet, and finally a little bit stronger yet, and finally, and then I might reach a scenario where it is all elastic. This was the basis of Dang-Vance criteria that I mentioned. Doesn't have to be all elastic. Well, I could reach the saturation stress and then get plastic deformation. If you test in a constant stress limit rather than a constant strain limit, then it loads up to some stress and you unload to that stress and then it's always elastic. That's an unrealistic scenario, but that's what would happen. The other thing that happens to materials, right, is the idea of kinematic hardening. And kinematic hardening, right, is that, all right, I load this and it has an initial yield point at A, the same as in the previous one, and now I plastically deform it here, and so I end up with some stress at B. And I write this in terms of sigma bar. This is the effective stress, so I could do this experiment however I wanted. I could do this experiment in tension, in torsion, or some combinations of tension and torsion, or any other load case that I chose. Right? And the idea of isotropic hardening is when I unload it, I will unload this, and when I reach a stress here, right, and this stress is equal to whatever the stress is here, minus twice whatever the original yield strength was, then I will start plastic deformation, and then I'll just deform this back to 0. And if we look at this in my funny plane, what it says is, I had an initial yield surface that looked like this. And when I started to plastically deform this, instead of the yield surface growing to get bigger, as it does in isotropic hardening, then this yield surface translates or is just moved like that. Right? Well, let's put a little physics behind that. Why does that happen, and why does this make sense? Right? So I have a little metal crystal. Right? So there's one of those crystals. And it will have a slip plane acting on that crystal. And on that slip plane, there will be some little dislocations, maybe like that. Right? A whole bunch of them, but there will be some dislocations. Right? And that's the natural state of the material. And now I pull this, right? And when I pull this, then these dislocations, if I pull this in tension like this, then these dislocations will all pile up on one side. Fine. And maybe I get some plastic deformation. But what would happen if instead of pulling this in tension, I push this in compression? Well, if I push this in compression, instead of all the dislocations piling up on this side, and remember these dislocations mean deformation. Remember when I showed you about dislocations moving out of the crystal when they had slip bands formation? It's really deforming. Now, if I push this in compression, they'll all pile up over here on the other side, and the deformation will be in the opposite direction. And if I look at that on my little diagram and said, okay, fine, if I load something in tension, I'm going out in this direction to this spot. But I could just as easily have gone off to this spot. Right? But look, this represents the elastic range, so that says I could go from here to here, and I'd have twice the elastic range. Because first, I could load this and move all the dislocations in this direction, right to the yield point. And then, I could load it in the other direction, and all these would move all the way across to the other side. So the range of elastic material, the range of elastic deformation, is always 2 times the yield strength. Because I have the range in tension and the range in compression. Okay? Now what happens with plastic deformation? Well, with plastic deformation, right, nothing more happens here. Right? These things are all stuck. So essentially, I'm going to grossly deform things and move it, right, to this new stress level. So there's just a higher stress here. than there was originally. But the range to move everything back here remains the same. And so what's happening in plasticity is a real material always has some combination of isotropic hardening and kinematic hardening, all going on at the same thing. And this behavior, right, is frequently called the Bowschiger effect. And that's what Bowschiger did with his funny mirror-based extensometer. He was measuring all of these things. So the elastic range is only twice as much. And the nomenclature that everyone uses in plasticity is we call the center of this yield surface, we always call that alpha. So alpha moves around in space. The other kind of behavior you can have is you can have ratcheting, and that's what I showed you from the equations. I have a bar, and if I put a tension load on this bar, and then I simply twist it, with every twisting load cycle, it gets longer and longer and longer, and that's actually what you see. So ratcheting is a big problem in railroad rails because you have all the deformation in one web. The railroads would be better if they alternated the trains going one direction and the other direction than if they all go in the same direction. For that, by the way. Another thing that you get in materials, so we look at the stresses and strains, then if we load something and we have a high value of the stress, when we unload this, the stress will tend to relax a little bit, and then with subsequent loading, the stresses will not return to the original stress. It'll be a little bit less. And so there's a tendency with plastic deformation for the mean stresses always to approach zero. So if you look at what happens in a material, and I now want to model what happens in the material, then I have to model the isotropic hardening, I have to model the kinematic hardening, I have to model the ratcheting behavior, and I have to model the mean stress relaxation. And that goes on inside the models. There's cyclic creep. That's the same as mean stress relaxation, except it's controlling constant stresses rather than constant strains. And as you test something between constant stress limits, if those limits are not symmetric, then it gets longer and longer and longer with the layers. Right? So now I'm going to teach you 2 years of graduate school. I'm going to teach you 1 year of theory of elasticity and 1 year of theory of plasticity. And I'm going to do it with 2 PowerPoint slides. One of my favorite cartoons from Scientific American is a cartoon with the professor in his white coat starting off in the blackboard, okay, and he starts off in the upper left-hand corner of the blackboard and completely fills the blackboard, and as a couple of cartoons go on, and finally arrives at the end, and at the end, after all this mathematics, the professor turns around to the class and said, "A miracle occurs," and he writes E equals mc squared as the end. That's what I'm going to do. Okay, I'm going to take the 2 years of graduate school, and a miracle appears, and I'm going to give you the answer in it and show you about plasticity models, just conceptually how they work. All right? Because that's all we need. And I do this because I believe what Jenkins said in the first slide. I believe to understand fatigue, we have to understand what the stresses are. And I don't know the stresses when there's elastic plastic deformation. I have to calculate them somehow. And this is how that's done. So now think about, I have the material. And now I talked about yield surfaces, but I could have these funny little surfaces. Remember, this is just the tension stress, and this is the shear stress acting on the plane. And this represents the combination of stresses that are required to yield the material. But the yield surface concept works for other strains. So for example, I could say, fine, this is the combination of stresses that cause initial yielding. This is the combination of stresses that result in 1% strain. And this is all the combination of stresses that result in 2% strain. Right? There's no problem doing that at all. Right? So I don't have to use Mises criteria and restrict this only for elastic behavior. Right? So that's how the material starts. And now however I want to do this, pulling this, twisting this, or some combinations of pulling and twisting, let's just deform something. And of course I'll just load something and unload it. And we'll see what's happening inside the model. So I initially load this, and when I initially load this, I'll load here to point A. And of course, if I really was doing this, then of course I'd have many of these surfaces so that I got more or less a continuous curve. And I'm just using 3 of them, so it's a rather crude model. And I get to point A, and that's essentially, I'm going to load off in this direction. Of course, everything is elastic, so I know all the stresses and strains. And then, as I move from point A to point B, right, when I move from point A to B, I'm still loading in this direction. And you can see what happens is I'm now in the surface between first one and the second one. And so the tangent modulus will be lower than the elastic modulus. And I'm going to drag this yield surface along. And so I have the kinematic hardening part. And then I load this into point C, and that's up here. And now I'm going to drag the second surface as well, and I'm going to have a slope which is a little bit less than the tangent modulus. And I'm essentially going to stack up all of these different surfaces in one direction. Now, if I want, I could add isotropic hardening as well. This is the kinematic hardening part. And in the isotropic hardening model, then these things are expanding at the same time that they are moving. I don't show that because then it just makes the diagrams confusing. So now I'm sitting at this point C, and now I'm going to unload it. And I'm going to unload it along this path in the reverse direction. And you can see I dragged all of these surfaces in one direction, so when I unload it, the elastic range is doubled. And so I get double the elastic range out of it. But not only has the elastic range doubled, so has this range between the first and second surface. And so then I traverse across this way, and that gives me this. And of course, when I'm doing that, then this surface begins to translate in the opposite direction. And so this surface, if I were to plot alpha, alpha is essentially moving out this way, and moving out this way, and moving out this way. Now it starts to move back in the other direction. And then finally I end up at point F, and they're all moving in the other direction. And that's the basis of all the plasticity models. That's basically how they work. Right? And why is it needed? It's needed for the reason of Jenkins, that if I want to know what happens, depending on what the sequence of loading is, I could have any stress. Right? And that is, if I look at, for example, this point, all the stresses are compressive. So any little microcracks that are there are going to be held closed, even though the strains are in tension. Same thing if I pick this spot, as I mentioned before. If I'm at this spot, the stresses are popping everything open. So in order to understand about the T, I need to understand what are the real stresses. And I'll show you examples where that's important. Okay. So here's the second slide of the plasticity stuff. Right? So, yeah, you need a flow rule and you need a hardening rule. There's a relationship between the plastic strains and the stresses. Now, these are this is a constant depending upon what the material is, and this is the yield function, for example, the Mises function. And you can see it's all these partial derivatives, right? And of course, if I expand this out, I could take the next hour and fill the slides full of mathematics. Right? If we did that, then you would all be sleeping, and so that's kind of a waste of time, and so I don't even try. Right? Well, no, what would really happen is somebody in the audience would be paying attention, and, you know, I would not be. Just like when I was writing them all, so there would be a few mistakes here and there, and so, yeah, it's... There are always some students who like to find a mistake in the professor's slides. I've never understood that logic, you know? Because I have to end up assigning a grade at the end of the semester, so why, you know, I mean, here's this person who's been bothering me all semester, and I have the final examination to grade, you know? And then I have to assign some points at the end. Well, I don't know, is that a mistake? Oh, well, it's not exactly right, and okay, -5, you know? And it's just human nature. So, anyway, be that as it may. Look, here's what this really means, right? In that I'm sitting here, right? And here's my circles we've been talking about, and I have a current stress point. when I deform it, what direction will the stresses go? Do they go in the same direction of loading? And the answer is no. Right? The answer is no. And that's my experiment. If I put a static tension on here and then I twist it a little bit, right, what happens? Well, this actually gets longer, and that's that coupling between the tension and torsion loads. Right? So when I'm at this point and I load it, then maybe these stresses go off there. Right? So I need some rules for that. Those rules essentially are given by that. So that's the first part. And that's the flow rule. And of course, when you go to the International Journal of Plasticity, then of course, people write an awful lot about the exact details of this because they are important. And if you ever try to program and implement this, then there are all kinds of numerical issues that go into here as well. So I don't want to make fun of how much work it is. I mean, they are interesting subjects, but for our purpose, right, we're only interested in the answer for fatigue, so I never get off. The second thing that happens is you have a hardening rule, and that is I need to know how does this circle grow for the isotropic hardening, and how does it move? And just like the stresses don't move necessarily in the same direction as the loads, the center of this surface doesn't move in the same direction as a vector coming from the origin. It can move in some complicated way. And so I have a hardening rule, and the hardening rule also has some function of this current stresses and the plastic strength. And again, the International Journal of Plasticity is filled full of papers about the nuances of all these rules and so on. But there's really two parts to it, right? One part's the flow rule, what direction do the stresses go, and the other one is how does this surface translate? And of course, there are many models that don't require a surface, so-called unified models, and so there are lots of variants. Okay. But that's the basic idea behind it. At the end of the day, we can do stress-strain response pretty reasonably. I don't, at this point, have a comparison of the calculations or experiment, but this one, just to show you, although we have a bunch of this kind of stuff, this is just a simple tension torsion history. Right? I start and I pull this out in tension, and after I pull this in tension, then I just do a twisting cycle, and then I unload this back to zero. And now I twist it, and then I do a tension cycle, back and forth. Same thing here, I push it in compression, and I do a torsion cycle, come back. I twist it in the opposite direction, and then do a tension cycle. And while this looks pretty simple, right? And after all I did was pull it like this and twist it, and so on. This is what the stress response looks like. Yeah, a little bit complicated, but it's easy enough for us to. It's easy enough for us to. You can see certain features in here. Of course, you can see the features that I pulled this in tension, and so I have a mean stress here, and I twisted it here like that. And you can also see other features, like here's the interaction of the tension and torsion loads in it. And the other thing you can see is that with time, you can see this thing actually growing, right? This was the initial cycle, and later it's just grown and become bigger and bigger, so that's all that sphere getting bigger. So they work. I consume too many hours doing this kind of stuff. And there's what the individual stresses look like if I were to plot the stresses in the XY system. All right. Okay, so just a summary now on the behavior of materials for stress-strain response, the kinds of things that can happen when you have plastic deformation. And so I talked about the isotropic hardening and kinematic hardening. You can get cyclic creep or ratcheting, mean stress relaxation. And the thing I have not talked about is there's a special kind of hardening that happens which is only found in some non-proportional loading histories. And I will talk about that later when I talk about non-proportional. All right, so I have talked for a long time, so this would be a good place to take our break. You are tired of listening, and I'm tired of talking. Yeah, we've had enough.